you. I do actually have an internet presence, but you have to go kind of far back, and I can assure you there is some weird stuff. So maybe don't search, but if you're interested. I'm going to be talking about the oracle at Delphi neither speaks nor conceals. And this picture is a clue to what this talk's actually going to be about, if you recognise it. But before we get into that, I'm Sam Galson. I work for YLD, a software consultancy. Follow me on Twitter, read my blog posts. I try to make them interesting. So, what this talk is not about, Oracle, and if you recognise the logo below, my commiserations, it's not about that either. What it is about is something called the Oracle problem. What is the Oracle problem? So you might be familiar with the term Oracle if you've read about Turing machines. So in that context, an Oracle is some piece of information that you feed a Turing machine, which allows it to decide on a problem, but the key point is that that information comes from some source outside the Turing machine, so the Turing machine couldn't have known about it, which is why it's called an Oracle. It's also used in the literature on testing. So we have these things that we call test oracles. And a test oracle is some piece of information that you feed your program, which allows you, it's an external piece of information, it's something your code doesn't know about, but it allows you to decide, it allows the computer to decide whether your test has passed or failed. So you've probably all written thousands of tests like this. This is a test oracle, so there's three parts to it. There's a bit where you create your expectation. There's a bit where you run the program to generate an actual result. And then there's a bit where you compare, so you compare your expectation with the result and say, did that pass or not? This is also an oracle. Anyone recognize this figure? Put your hand up. Okay, you need to go read some ancient Greek. This is the oracle at Delphi. She was called the Pythia, and she would sit on a vent of noxious fumes and spout forth the prophecies of the god Apollo. There's lots of stories about the Pythia, but one of the key things about her is what the philosopher Heraclitus said, which is that the god whose oracle is at Delphi, neither speaks nor conceals, but gives a sign. Okay, what does he mean by that? Well, to give you an example, the Greeks used to illustrate this with the story of the rich king Croesus. Now, Croesus was this king in Asia Minor who was very interested in oracles, and he wanted to expand his empire, so he went to the oracle and said, if I invade the Persians, what will happen? And the oracle said, if you invade the Persian empire, a great empire will fall. And of course, Croesus was like, great, let's go. And you know, the oracle doesn't speak. The empire turned out to be his own. And we face a similar problem with test oracles because our oracle is only ever a partial representation of the system that we actually want to test. Right? Usually we're testing with a single input. Usually we're making a single assertion and testing against a single output. In some cases, we don't even know what output to expect from our program. And this is the oracle problem. So what can we do about it? The answer lies in the concept of fuzz. Put your hand up if you know what fuzz testing is. So a fair few, okay. If you've used fuzz testing on a JavaScript project, leave your hand up. Okay, 3 or so. What is fuzz testing? Is a fuzzy term itself. It encompasses a lot of different testing techniques, but the basic idea behind them all is that instead of using a test oracle that we write, we generate them automatically, which means we can have hundreds or thousands of these test oracles. This obviously doesn't solve the oracle problem. Okay, we're never going to predict the future entirely, but it's a mitigation. Now, there are many kinds of fuzzing, as I mentioned. I'll describe what these are, but I should explain that my reasoning for wanting to do this talk is that, first of all, I don't think the knowledge around these different kinds of testing is that great in the JavaScript community compared to in some other communities. And I genuinely don't know exactly why that is. I don't know why fuzzing hasn't quite caught on in JavaScript. It could be that it's not useful, in which case I'm interested in hearing opinions on that. But there are a number of libraries which have started to emerge recently which have made various styles of this testing possible. So I think it's worth looking at these libraries and evaluating if they are in fact useful for JavaScript developers. So let's have a look and see what these kinds of testing actually involve. The first thing you can do is cheat. So you can get this thing called the big list of naughty strings from GitHub. Now, instead of writing one test with a string that might, instead of writing a test to check that, say, your API processes a user called John, you can now fire hundreds of usernames, some of them containing naughty stuff like instructions to drop table, and see if your API can cope with this. There's a really easy way to do this. You just install Artillery, which is a load testing framework, and this plugin. And then Artillery you configure with YAML. You just write this piece of YAML. It says, fire at my session endpoint, a username and a password, but do this hundreds of times and take a different naughty string each time you do it. This will take you like five minutes to set up. And the result is you can avoid bugs like this. So this, I don't know if you remember this, it was some time ago. Basically, everyone on Twitter kind of simultaneously realized they could break Jira if they put an emoji in the right field. This is one of those rare bugs that actually makes the world a better place. But they could have avoided this if they had just set up Artillery to test with the big list of naughty strings. Okay, now what about blind fuzzing? What blind fuzzing involves is, this is now not cheating, this is true fuzzing, because we're actually going to generate random mutations of some test data, and we're going to do so blindly, which means we're going to use various strategies to vary the bits in a kind of a random fashion. And there's a couple of tools you can use to do this. Redamser and Zuff are some of the main ones. As you can see, it's very, very easy to use. The key point is that each mutation, so here we're just going to produce 100 bits of random data, or 100 mutations of the word hello. And each mutation has a seed, which means it's deterministic. So if you find one that causes a bug, you can easily recreate it. And the output is something like this. So it doesn't crash the terminal, so that's good. The terminal has a nice fallback for displaying bits that it doesn't understand, which is the question mark. Okay, now the standard way people think about fuzzing, if it is something on their radar, is it's something that's useful for testing when we don't. It's not simply that we want more test oracles; it's that we can't think of a test oracle at all. Either because we're working with a legacy API and we don't know what it's supposed to do, so how can we test it? Or we're working with something very complicated, machine learning cryptography, where the output is just so hard to predict we can't really write tests. This, I think, is kind of an old-fashioned view about what fuzzing is good for. There are some voices now, which is worth pointing out as well. So in this model, the way you do fuzzing is you fire random inputs to your application, and you basically watch it for crashes. So the thing you're monitoring is whether or not the application crashes. And historically, this is thought to have been most useful for stuff like C, where there's a high chance of issues managing memory and stuff like that could cause crashes. And indeed, that is still the main application for fuzzing. But there's some interesting stuff that's been written on this by Mozilla, who are heavy users of fuzzing. In particular, the value of assertions in your code. So if you put lots of assertions in your code, and then to do the same process, you can watch for much more interesting things than just crashes. And you can actually use this kind of random input testing to uncover business logic faults. How can we do this in JavaScript? Well, of course we can. We've got sync dweller, which is just a very simple wrapper for Redamser. As you can see, it works very similarly to Zuff. We set a seed, we pass it some data, we're passing in a buffer of hello, and we just fuzz that 100 times. The author of sync dweller also has made this nice fuzz me maybe module, which allows you to control where you want the fuzzing injected in your application. So you can insert this, you can wrap anything in this fuzzer and then control whether or not you want the fuzzing to actually happen using an environment variable. Okay, and the output of Redamser is stuff like this. It's just interesting to see this because it's so different to the output you get from Zuff. So it's worth being aware of that different fuzzing algorithms produce different sorts of results. Now, what's the next step up in terms of sophistication? These things called genetic fuzzers. The oldest and most well-known of these is AFL, which stands for American Fuzzy Lop. And what does this do that's different? Well, it has this very simple algorithm where it feeds the fuzzed input in, and then it does an extra thing, which is it checks whether or not that input increased coverage. What this means is that although it's working in a kind of a blind fashion in the way it fuzzes, it keeps track of those inputs which are more likely to reach further into your application and therefore more likely to discover edge cases. So it results in much faster results. It looks like this when you run it. Now the problem with AFL is it was written for C. And if you want to use it, you have to compile your C program with some special stuff to get the coverage, and then you can fuzz it with AFL. So if you want to use it in JavaScript or Python or whatever, you have to write a separate implementation for those languages. And there are some pretty popular AFL libraries in Go, AFL in Rust, and even in Python, where the library there is fairly stable, definitely usable. In JavaScript, we don't really have one. So there is this library, it's the only one I could find, JS-fuzz. It kind of works, it's a bit buggy. I think it's a great thing to work on to help bring us, again, one of my main messages in this talk is we don't want to let the Pythonistas beat us with this kind of stuff. Like, if they've got one, then we should have one too. So, yeah, get to work. Right, what's the next step up in sophistication? Again, we open our eyes. We're no longer blind fuzzing. This is what my parents always told me. I don't know if it's true. We can use a grammar. There's a few fuzzers that will allow you to do this. I recommend starting with Dharma, which is maintained by Mozilla. Grammars look like this. So this is a complete grammar to specify URL. You can use this to have your fuzzer automatically generate as many URLs as you want, and you can be sure that they'll be valid URLs. This is obviously going to vastly narrow down the number of test cases you need to try. At the same time, it's less likely to discover some of those more extreme edge cases, but it's worth being aware of as a strategy. But where's our JavaScript? Okay, if we can generate URLs, why can't we just generate JavaScript objects? Of course we can. Another library by Mozilla can help you do this. So just various helper functions for generating random JavaScript objects. And this isn't random in the sense of faker or something like that. If you've used that, where it's kind of random realistic, this is random, let's try and break your application random. It comes out looking something like this. We can also use this library, fuzzer, and just pass in a whole object, and it will fuzz all the keys on that object. But once we've got this ability to create fuzzy data within JavaScript, actually a whole new vista of the kinds of tests we can do opens up. And we can do this thing called generative or property-based testing. And the idea of this is that instead of fuzzing some entry point to our application, like an API or a standard input, we can actually fuzz individual functions. Now, property-based testing libraries are actually core components of various different programming languages, maybe most famously Clojure, or at least they talk about it a lot. If you look in the Clojure docs, you can find statements like this. Property-based generative testing, as implemented for Clojure and test.check, has proved to be far more powerful than manually written tests. Is that... okay, powerful, who knows what that really means. But, I mean, is that true? If so, shouldn't this be something we're looking into in JavaScript? And again, we do have libraries for this, and they're much better. They're in a much better state than the AFL library I mentioned earlier. You can actually use them in production if you want. However, they're nowhere near up to the standard of libraries in other languages like Python yet. Here's an example of what it looks like. So let's say we've got this stupid add 10 max function where we want to add something unless it's more than 10, in which case we'll just return 10. But I was so bored by this function that I forgot to uncomment the line that actually makes it work. How can we test this? Now, we're not going to test it with a single input. We're going to test it with a large number of random inputs. So we're going to need to specify the type of those inputs. So we say gen.int, and the framework will just run this loads of times, and each time we'll run our assertion. And we can do it in a nicer way as well. There's plugins to work with various different testing frameworks. So all we have to do is we can have our ordinary jest style test, just pass in a couple of extra arguments for our generators. And there's a whole bunch of different kinds of stuff you can generate. Not just JavaScript types, but also sort of subtypes, I guess, like positive or negative integers. And you can write your own generators if you want. And it comes with this function sample, which allows you to sample your generator. And this is an example of a JSON object that it will give you. Now, these property-based testing libraries come with a rather clever feature called shrinking, which was originally written for the Haskell property-based testing library. And what it does is, so this is the result of the test I showed you earlier. So it came up with a random input 21 and 8, and it found that the assertion failed. What it then did, using this shrinking technique, is it tried various inputs to try and work out what the smallest input it could give the function was, which would cause the function to still fail. Then it worked out that anything lower than 3 or 8 would fail. So 3 or 8 sides is the minimum input. And this is incredibly useful if you're trying to work out what the actual bug is in your code. So if you want to use this, one of the annoying things is unless you're using TypeScript, maybe you like JavaScript because you don't have to write types. Now you do. But if you are using some typing, then why not just infer your generators from your types? This is the only library I found that actually enables you to do this, and it's for Flow. I haven't found one for TypeScript. I'd be curious to know if there is one. It works like this, so you have your Flow type, and it's a Babel plugin, and it just converts it into a function which returns a generator for that type. So we've got a person with a username, password, age, and this is what it gives us. This library hasn't been updated in 2 years. It's got various to-dos associated with it, but I think this is an interesting area for people to work on. There's also this one called Juzz for joy. So you can pass it a joy schema, and it will use that as a generator. So it will respect things like your minimum and your maximum, and it will respect various other restrictions you put on your joy schema. It's not mature, and it's also not a property-based testing library, it's just a generator. So you're going to have to write a custom generator for one of the other libraries and plug this in if you want to use it. But it could be a really cool way of testing your API endpoints if you use Joy. So writing types is just part of the picture. Actually, the really hard thing is identifying properties, because you have to identify properties that will hold true no matter what input the function is given. And that can be a bit tricky. I'm not going to talk too long about this, but to give you an example, if you have an encode and a decode function, you can just encode and then decode and check that the output is the same, and that's a property that's going to be invariant. But there's various categories you can use to help think about this and help identify properties. Right, I also want to mention this library, FastCheck. FastCheck is written by Lee Byron at Facebook, and it introduces kind of an additional feature which is really interesting and I think useful. So it's called model-based tests, and it's for testing systems that have state, such as UIs. And the way it works is basically your random input, instead of being some kind of data type, is an operation. So you define an operation like login. You define a precondition for the operation like has to be on the login page. And then you define a postcondition, which is an assertion. So if I've done this operation, then my state should reflect the fact that the user is logged in. And this is great for catching those types of bugs that you get in UIs where, for example, if I navigate to the login page and log in, everything's fine. But if I go to the about page and then to this other page and then to the login page, for some reason, I have no idea why now it doesn't work. Because what this will do is take your list of operations and create random permutations of them and try them all and see if any of them break. And this library might be incorporated into Jest at some point. Okay, so what are the problems with these Oracle problem solutions? The first one is they need lots of computing power. Well, this isn't so much a problem today as it used to be. And there are various solutions if you really need hardcore computing power. That last one is particularly interesting because they're promising a JavaScript implementation of AFL, but it's a paid service, so I don't know if it's going to be open source. OSS Fuzz is for big open source projects, and there's a currently private service by Microsoft, but there's also some open source stuff you can look at. The real problem with these Oracle problem solutions is that fuzz testing is not really well understood. As you've seen, the tooling is kind of intuit and needs work. And most significantly, the payoff is unknown. Like, we really often don't know, there isn't enough expertise within our organizations to say whether or not it's worth investing potentially a lot of time into setting up these various kinds of testing. And if you think about it, what that is another Oracle problem, right? How do we evaluate whether or not our tests, how do we test whether or not our tests were worthwhile? Okay, so it's the Oracle problem, but this too has a solution. That solution is mutants. There is something called mutation testing. And mutation testing is basically coverage on steroids. So coverage checks whether or not your code has been executed. Crucially, it does not test whether or not that code has been asserted upon, which is why it's a notoriously unreliable guide to code quality. Mutation testing is designed to do just that. So how does it work? Instead of mutating your input, it mutates your actual code. So it will do stuff like alter return values in your functions, it will change comparison operators to inequality operators, and then it will check whether the changes that it made caused your tests to fail. If it completely messed up your code base and none of your tests fail, then your tests probably aren't that good. I think this is a really exciting kind of development for some of the tooling and testing in JavaScript, and I'd like to see people adopt it so we can work out if even this mutation testing is useful for JavaScript. Currently, there's only really one library which allows you to do it. I wouldn't say it's mature, but it's got quite a lot of effort behind it, so you can use it. You can definitely try it out now. I'd recommend it. Yeah, and let's work out whether fuzz testing is worthwhile. Thank you.